There, officially. So, Zoomers, you can hear me and see the screen? Roomers, you can hear me and see the screen? All right, we're here. We're doing this. Welcome back. I wanted to let you know about a couple of schedule changes that I decided on. Just a second here. There's my mouse. So first off, if you have not already done so, I have a new example 3 document that I finished yesterday. And so I have a handout for that and associated files. Those will be useful for your next homework, which is homework number 3. I decided to push that back a week because I wasn't sure how much we would get done tonight, and I didn't want to rush through things. I'd rather people feel better about their understanding before trying to attempt stuff on their own. I am pretty confident that I have more material to go through than we have time or patience. So I will make a video tomorrow morning that we can catch us up in terms of the remainder of it. Homework 3 then is actually already available. So if you would like to procrastinate on any other schoolwork or life work, like if there's a paper you don't want to write, a garage you don't want to sweep, something like that, I would encourage you to do homework number 3. So it is available in the online portal, same place where homework 1 and 2 was, and you should be able to access that. Let me know if you cannot or if you run into any problems. Then I pushed formative assessment 5 to be due the Sunday before spring break, but I will have that available way in advance. So you're not expected to do any sort of work on your official break. And I also posted the plan template for your project. Now, this is not due for several weeks. However, for a lot of folks, the issue will be figuring out what data you want to use. And that will likely involve conversations, potentially permission forms and things like that. So I wanted to put this up here. So this is available for download on the due date for the website. So right here, it will be submitted in Canvas. So that I use Canvas for collecting things. I will return it to you via the online homework system. And the main idea is that it's your chance to practice with the models we're talking about in class on data that you care about. Ideally, like I would like this to be the basis of something that could turn into a real research project, a poster, a presentation, even a manuscript, something like that. But if you're sitting there thinking, yeah, I have no idea what kind of data I can use, there's all kinds of public access databases that you can work with. And so I just listed a variety of those that people have found useful in the past. I would also encourage you to talk to your advisors, your program faculty, ask if they have quantitative data that would be amenable to a regression model that you can play with. Potentially, then you find yourself a new collaboration. So I am happy to help answer questions about what your data are, whether they can work for this. The main thing that will be tricky, I think, in practice, I have requirements down here, is 1 dimension of sampling in your data set. So that means like a cross-sectional study of units. So if you have repeated measures, you might have to use just 1 occasion. If you have, you could aggregate across repeated measures to like a mean or something like that. If you're not sure what to do, please talk to me over email, office hours, etc. I'm happy to help you try to figure this out. This doesn't have to be something you figure out on your own. This can be a conversation. So I wanted to put this up, even though it's not due for a while, to get folks thinking about it, and that way we have time to talk. So what I would like you to do is just literally type your answers into this document to 3 questions. Describe your sample, describe your variables, and tell me what you want to know about them. From there, I will weigh in. If it looks like everything is straightforward and we can readily envision what the models would look like to answer your questions, you'll get your credit, I'll give you feedback, and away you go. I expect that for at least a third of you, though, based on previous experience, I may need to ask additional questions to help you figure out what to do. In that case, you will get a chance to revise this document. That way we both have in writing a plan as to what you are planning to do. Does that seem fair? Okay, questions? Yes.
I had a question.
Yes, please.
If we were able to get consent forms from the school I'm working at, am I able to collect the data from where I'm working?
I can't tell you the answer to that without knowing more. If it's like your own students and you have access to them, and other than like parental consent or something, and you can fit it into what's already happening in your curriculum, then probably yes. But if it's an ask where you'd have to get someone else to let you do something, and that takes time or money or effort, then it may not be feasible. So this may be something that we have to talk about offline just to see what you're thinking of, unless you want to share more in this forum.
I don't want to waste everybody's time. Yeah,
It's not a waste of time. I just want to be sensitive that if you have specific people or things involved that you may not want that broadcast, that's all.
Yeah.
Fair enough. Yep, that is totally fine with me. I have had students use their outcome data from their students in these types of things as well. So end of year reports, progress measures, formative assessment measures, anything like that. If you want to actually analyze data from your own teaching or work experience, that's totally fine. It doesn't have to be necessarily research based, but something you care about. Because honestly, that is where the magic happens. Like I make up data sets about preschool and fits thrown and pleases heard because those are things that are fairly universal. But there's something different that happens when the X and Y is something that matter to you that I can't replicate in just canned data. So that's what my intention is to get you as far as we can in towards some type of project that you can eventually turn into something. So I will shut this down then unless there's any other thoughts or questions on that. All right, get rid of that. Okay, so then I was pleased to see that not only did everyone complete their formative assessment this week, but we had 100%. So it feels a little anticlimactic to go through it, given that everyone who would have made a mistake has already figured out what went wrong and fixed it. But are there any particular questions that folks want to go over or just hear, like, why is this right? That kind of thing. Do we like the format where there's immediate feedback and you get to fix it better? That was the consensus before. We're still happy with that? Okay, good. Does it make you redo the whole quiz if you want to just change one answer? Does it? Okay, so yeah, then, so there's enough annoyance that sort of makes it worth the effort, I think, to go back through and change what's wrong. I did turn on the correct answers, which you can infer based on your scores, but those are available just so that you can see those for future reference. I checked the settings for the other formative assessments, and it looks from my end like everybody can see everything. So if that is not true for you for a particular one, please send me an email and I will try to track down what happened. But from what I can see, it all looks like it's okay. All right, checking the recording. I think we're good on that. Can someone from Zoom please say hi real quick so I can see if it's being recorded?
Hi.
Okay, it's not according to that. Let me see if I can switch the source. Last time I noticed that it was had like an echo and I was trying to prevent that from happening again, but we'll see. All right, can we try it one more time?
Hi.
Okay, that may be, so that's what we got. Okay. Why is it not? Okay, we will see how that works. Okay. Where were we? Lecture 3. So we did a little bit of that in class last time, and I had recorded a video to get us a little bit further. Did folks get a chance to walk through that? Yes? Should we jump right into the questions then? And we'll see where we are with that. So I have a question slide on 13. Let me open up the whiteboard that I made for this unit, and we will spend a few minutes trying to answer the questions. So the topic is analyses with categorical predictors, more than just 2 categories. That should be loading. Okay. There we go. I see folks. I don't know why it sometimes shows the names and sometimes not, but it's only on my screen. It's not being recorded, so away we go. So we're at the first slide here. I don't think so. I think we figured that out last time. So I just zoomed in. Zoomers, can you confirm? Do you have your own like Zoom capability? Okay, cool. So you can make it as big or little as you need to. And I do know in the text boxes, you can drag those to make them bigger. So then you can scroll the font that way as well. Looks like the typing has slowed down a little bit. We could start to discuss. Noticing the answers are very spread out, so I'm doing a lot of scrolling here to fit them all in, but we got it. All right, first one then. So I have, I can't have the screen share open and the whiteboard open at the same time on the Zoom. So I'm just going to tell you what slide I'm referring to in terms of where the answers would be coming from. The first one on slide 5, in initially introducing what has to happen if your predictor has more than 2 categories, there is a formula by which to compute how many possible mean differences there are given the number of categories. So if we have 5 categories, then it takes 5 fixed effects in the model to make it so each category gets a distinct outcome mean. And those should exactly match what they are in the data when you just run descriptives. So we count 1 fixed intercept as what the mean would be for the reference category, which is something we choose. And then there would be C-1 slopes needed to differentiate the others. So for 5 categories, that would be 4 slopes, 5 fixed effects in total. That means then that 4 of the differences are given automatically. And under this type of coding scheme, scrolling ahead to slide 6, it's referred to as indicator coding in your textbook, and it is by far the most common thing that you will see. In this coding scheme, what you get by default as a model parameter is each group relative to the reference. And so then it would be like, if you set A as the reference, then it would be like B versus A, C versus A, D versus A, E versus A. But if the model tells you then how each group gets its own mean, it also tells you how each group gets a mean difference, because you can literally just subtract between the two in terms of the model parameters. So there was an example of that for 3 groups in the video that you watched, and then also extending that into 4 groups, for instance. So the same process would work for 5 groups. Figuring out how many extra comparisons you would have. I actually counted on my fingers just to make sure I had it right. So if anyone else did that, no judgment. If we have 5 categories and then 4 of the differences are given by the model, that leaves 6 other possible comparisons that you might want to make between pairs of categories. There are other kinds of comparisons you might want to make that lump categories together. So in the example 3, I'd have one of those just to show you what that would possibly be. So any questions on that so far? Then let's see, how many, the answers are 4 slopes, give 4 mean differences directly. There's 6 more mean differences between pairs that are indirect, as well as others that you could potentially ask for. And then how do you know that which category is the reference? It is up to you if the data are coded as numeric, and the way to set a category as the reference, such as on slide 11, is to make it the 0 group for all of the binary predictors that you create to differentiate each other category from the reference. So what reference is up to you. Those of you who are familiar with R or other software packages, do you know the term factor variable? So is there an analog in JMP? Do we know terminology? I know that's what most folks here have used before. Let me switch back to the screen share for a moment here. Nope, not that one. Factor variable is the term that I'm most familiar with. In SPSS, it would be like the fixed factors box or the by command in syntax. In Stata, it's IDOT. In SAS, it's a class variable. So most packages have this designation. And how you know what the reference category is depends on what the software defaults to. So in R, it is the first one as the default. The same is true in Stata. In SAS and SPSS, it's the last one, just because. So you won't necessarily know based on your output. There are, like I said, there are ways to sort of automate some of this process, and I think we had a question about that using EM means previously. I am deliberately not doing that. because I want you to understand how the model creates these things, because that then allows you to do so in non-standard cases. If you have a straightforward analysis of variance with one dimension, which is what we're talking about here, then you can click a box and get all possible mean differences. But if in a non-standard case where you have interaction terms or other types of covariates, in more extensive models, you have to do more of the work yourself. So I want you to understand sort of the underlying logic, and then once you get a hang on that, then you can look for shortcuts in your software to speed along the coding. But who the reference group is up to you, and you have to somehow figure that out if the software defaults to something without your permission. So questions or thoughts on that? Should we walk through the example? Or do you want to talk about sums of squares? Said no one ever. Maybe just review for a second. So I'll start with slide 6. We'll do a little bit of review here. All right, Zoomers, can you see the screen share still? We're still good? All right, make sure I'm still recording. Yes, I am. That's always good. Sometimes I forget to hit unpause. That's bad. Okay. So in this example, we only have 3 groups. That means one of the groups is the reference. That's the intercept. The intercept directly provides the expected outcome because that is when the predictors are all coded 0. So the rules are the same regardless of whether you're talking about groups or whether you're talking about numbers. In this case, then the other two groups means is formed as linear combinations of the intercept plus the effect of the slope that differentiates that group from the reference. So for instance, the middle group versus lower here, the upper group versus lower here. So because the model tells us how to find the mean for each other group, it tells us how to find all the mean differences. So in this case, 2 are direct, meaning they're given directly by the slopes all by themselves. The third is a linear combination of the difference between the slopes. So in code, the first thing that you would need to do is create the new binary predictor variables. And in this case, we designated the first category as the reference. And so the 2 new binary variables are coded 0. That's at the end of here. So we read this from the inside out. So if this original variable called working class is 1, then first new one goes to 0, the second new one goes to 0. And by the way, LVM and LVU are because the groups were called lower, middle, and upper. Name them however you like. I have a slightly longer name in the example just to make that point. Same thing then for if the original variable is 2, turn the first one on to 1, and if the original variable is 3, turn the next one on. And so then we have output that looks like this, where all of the terms are significant, meaning that the intercept for the low group, the amount of money that they make on average, is significantly greater than 0. I would hope so. If you're in the middle group, you make more money by $8,800 than the lower group. And if you're in the upper group, you make about $11,000 more than the lower group. What we don't know is whether middle and upper differ significantly from each other. And we cannot infer that they would or would not, because we don't know what the standard error would be for that remaining difference. And as we talked about last time, the upper group only has 20 people in it. So any comparison of that is going to be noisier, more inconsistent across samples, higher standard error as a result. So that's where our friend GLHT, General Linear Hypothesis Test, from the MOLTCOM package, is used to make any kind of linear combination of fixed effects that's not directly given by the model. Predicted values is one instance, so the 3 different possible predicted incomes based on which category you're in are 3 things that I asked for, noting that one of them is already in the model. And then the 2 differences that are implied by the model along with the third. So what this code here is doing with the minus sign is subtracting. So this is beta 2 minus beta 1, where each of these values are in order of the fixed effects of the model. So then that gives us the rest of the information. So your readers would want to know like these 6 numbers, like you would make a table for your results section with these things and then walk them through which groups were different. And lo and behold, middle versus upper, even though upper makes more money by about $2,000, the difference between these 2 slopes, that 2,000 is not different than 0. It's not significant because the standard error for it is much bigger. So as a ratio of signal to noise, the signal is 2, the noise is 3. So that creates a T ratio of well inside the boundaries of 2-ish that would typically be used for declaring significance at an alpha of 0.05. So, yeah, so then here's everything I just said written a little bit more neatly in that slide. And here's a picture. I don't know if this helps or not, or if it makes it worse, but I was trying to locate 2 different x-axes onto the plot to illustrate how this works. So if you think about a slope as the change in y for a 1-unit change in x, or rise over run, you can still do that, just with the idea that you're going from a 0 group to a 1 group for the red part here, and then the 0 group to the 1 group for the blue part here. So you can figure out the differences that are implied by the model by the differences in these 2 heights right here for what the change in y is going to be. Question was, can I describe the threshold for standard error? Is it only in reference to the estimate? Yes, it is. So just to review, estimate is in terms of change in y for units of, or 1 unit change of x. Standard error is also, the numerator of it is the residual variance, essentially, is what goes into the numerator, which is units of y. And then the denominator is the variance of x, so units of x. So it's like both of these things, estimate and standard error, are basically like y over x. When you take estimate and divide by standard error, it flips it upside down, and so then the units cancel. So then what's left is t tells you in a standardized way how many standard errors or standard deviations in the sampling distribution away you are from the null hypothesis. And so t value of like plus or minus 2-ish tends to be where the boundaries are, where 5% on the outside starts, and that's where we would declare it to be sufficiently unexpected if the null hypothesis were 0. Does that help? Who knows? Okay, please keep the questions coming. You can ask them out loud. You can type to me in the Zoom. You can do whatever you need to do. I'll take sign language too. I talk with my hands a whole lot. All right. So 4 categories. We walk through this. By the way, homework 3 is 4 categories. You get to apply this. So this is like a generic abstract version, but the code works exactly the same. So instead of making 2 variables, I would make 3. And I would follow this type of coding system in designating the 3rd variable. So it works like this. By the way, the topic of your homework 3 is about mini golf. It comes from a true story. I have a control group that has received no golf training of any kind, a treatment group that receives only mini golf instruction, another treatment group that receives only regular golf instruction, and a 4th that gets both. And this homework came about from a true story. My then boyfriend, now husband, when I went to visit his family for the first time in Sacramento, he took us out to play mini golf as an activity. I had no idea what cutthroat mini golf was until I participated in this outing. Like, this gentle, mild person was like talking smack to his sisters. And I was like, who is this guy taking mini golf this seriously? So that was one thing. And then we went mini golfing with my family. And my dad was blaming his poor performance as interference from his regular golf game. Turns out there are different skills involved in different kinds of golf. I don't care for either of them, but this is just what I've been told. So I built this into a homework problem where we're examining the interference effects of regular golf in performance on mini golf. And I'm bringing this up, I'll bring this up a couple different times because folks in the past have stumbled on this aspect. In golf, are higher scores better or lower scores better? Lower, yeah, okay. So a good outcome is a lower total score, meaning it took you fewer tries to get the ball in the hole. And I know that sounds a little bit backwards, but there are lots and lots of outcomes that we study in the social sciences where more is bad, like delinquency rates, disease rates, poverty rates, anxiety, depression, stress. Like, there's a lot of things where more is bad. So if you think of it from that lens, then it seems like a reasonable thing to do. But just to plant that seed that lower is better in golf. So hope you can have fun with that. All right, I did this already. Did that already. Okay, now we're back to sums of squares. Can I get a thumb check as to how much you want to review this? Where all the way up is like this. I feel okay with it as here, and no, skip it ahead. It's down here. Okay, modal response is sort of sideways here. So that means maybe not verbatim, but the big picture is here. So up to this point, there's a table that I kept saying, don't pay attention to that in the output. We're at the point where we pay attention to that. It's the idea of how do we assess as a whole how well the model works. And we haven't needed to do this up to this point because we only had one slope in the model. So the slope was the model, it was one and the same. But in these types of models where now I have two slopes, because I have three categories to differentiate, and in other situations in which you have multiple slopes operating together, a natural question is how effective are they at predicting this outcome? So a more general answer besides, is this group different than that group? Is this group different than that group? Is, do the groups differ, period, in this outcome? And that is the type of language that we would use in talking about this as an analysis of variance. What is the overall, or omnibus is the vocabulary word that shows up in that context. Omnibus meaning overall effective group. How much do the groups differ from each other? You can say that a couple different ways. One is the variance of the e's, so these e residual, how wrong the model is, does that get collectively smaller after we add these predictors than before? Or we can think about what the model says the predicted outcome should be based on the beta fixed effects, and is that predicted outcome, denoted y hat, significantly related to the real one, just denoted y? So this is a more general procedure that's called a multivariate wald test, and it's used in a whole lot of situations. This is your first chance to see it at work in this context. To do so, we got to have some new vocabulary. Degrees of freedom. Think of this as like points. So back in the 1980s, I'm dating myself here, Richard Simmons had something called Deal-A-Meal. He had like a wallet. Okay, a few of you are nodding. It was like a wallet of food cards. And you started out your day with all the food cards on one side, and as you ate something, you moved them to the other side, and when that side was empty, you put the fork down and you don't get any more food that day. And it was all about that. That's Weight Watchers points, right? It's the same principle. Calories in, calories out. Well, think of this as like points for your data. You have a finite number of points that you can spend, and that is your sample size. Because you know how I could get perfect prediction of my outcome? Let's say I have 100 people in my sample. You know I could get perfect prediction? Think of ID as a categorical predictor. I could put in 99 binary contrasts for me versus you, versus you, versus you, versus you, and everybody, and that would perfectly predict the outcome. Is that useful in any way, shape, or form? Is that generalizable to new people? No. But it would explain everything. So if we start with that as sort of like the upper limit of what we can do, then the question is, how effective is our model relative to the points that we have left over that we haven't spent? So the term for points in statistics is degrees of freedom. Degrees of freedom numerator, as it is going to be called, is the number of slopes in your model. So it's k minus 1 because k is the number of fixed effects, which includes the intercept. So it's number of slopes. Basically, how many points did you spend to build your model? That is going to be relative to how many points are left over, not yet spent. So if I have 100 people and I have two predictors in my model, I should have degrees of freedom denominator of 97 because I have 3 fixed effects, 2 of which are slopes. So that's one new piece of vocabulary. Number of slopes relative to number of slopes I could have spent, degrees of freedom. Then we have something called sums of squares. And this would look familiar because it is the numerator of the formula for variance. And overall, we start with how different each person's outcome is relative to the mean as like the total amount of information that's in this outcome. And I'm going to use the word information because variance has a denominator and I don't want to mix those two up. So we're going to basically carve up the information that's in our model into piles and then judge how effective that information is relative to the number of slopes that it took to get there. So we're going to have a model pile, we're going to have an error pile. The model pile, the information that goes into that is how much better or how much different, let's put it that way, how much different did we do relative to a naive model where everybody just gets the mean and that's it? How much additional information have we introduced by putting in these slopes that help people spread out on our outcome based on their levels of the predictors? So that's y hat minus y bar. Like, what is your current prediction minus the naive best guess from just the empty model? And then we divide that by the number of slopes that it took to get that level of prediction. So this is like what we got, what we spent our points on, how well did we do? That is relative to, what if we had just like put in random stuff? Like, what would you get sort of by chance? And that's quantified as residual or error sums of squares, where the information left over is what's relevant. So how different each person's score is from the score predicted by the model, y hat, and then divided by how many slopes you could have spent left over as a function of your sample size. So it gets summarized in a table like this. And when I was an undergraduate, like, this was a test question. Basically, they give me some parts of the table and have me fill in the others. And that's how I learned it. And it wasn't until I started teaching this that I started thinking about more real world analogies for this. So if you're not somebody who loves sums of squares, can we talk about Kohl's department store instead? Okay, doesn't matter if you shop there or not. You all know what stores are, right? Well, Kohl's has a special place in my heart. They had one in Coralville, Iowa, where I used to live. They had one in Omaha, where my parents live. Kohl's is everywhere. Anderson, of course, is the closest Kohl's that we have here. I love Kohl's because if you pay full price for something, you are doing it wrong. Like, that is not even possible inside a Kohl's. Because whenever you buy something, they give you more money, but you can't spend that money today. You have to come back next week and spend more money. And it's always like, the price tags are never the real price tags. There's always sales and clearances and things. And sometimes they have a machine that you can beep to see what the actual money is, but otherwise it's just a complete surprise. So it's difficult to ascertain how much money something actually costs. That doesn't stop people like my mother from emerging victorious when they feel like they've gotten a really good deal. So she will call me up on a Sunday and say, I went to Kohl's today and you'll never believe how good I did, right? Like, she approaches it like it's a skill, like an experience she's honed, how good I did. She'll list off the things she bought. I got some new socks for your dad, and I found the cutest top for Huey, and I got this new pair of pants for me that I really wanted, and you won't believe what I spent. I only spent $21, Lisa, and like, she's very proud of herself for this. So the way that I think about this is, the test of the model is, did you get a good deal? In order to know that, you have to quantify what's a good deal. So for her, it's like, how much did it cost? So that's like sums of squares model, divided by how many things you purchased. Like, what was the cost per item, essentially? So that gives you mean square model. So how much did you spend divided by how many things you got? But just knowing that in isolation doesn't help you, because it's like, well, is $21 for 3 things good? Like, what did the rest of the store cost? It's only a good deal if you did better than expected based on the rest of the stuff still on the racks. So that's where the rest of the store is like residual or error. This is like, how much would it have cost to buy everything that's left divided by the number of things that are left? And that's mean square residual. So if your ratio of dollars spent to things bought is better than the store's leftover ratio of inventory relative to number of things, then you win, and that's a good deal. And there is a way to quantify this as our new friend, F. Best statistic. F is T's cousin. Actually, I'm going to go with parent. We're going to go with familial analogies, because T squared is F if you're testing one thing. So F is a ratio of mean square model to mean square residual. How much did you spend relative to what's left over? You can think about F a couple different ways. It is also written as a function of something called R square, which is defined as sums of squares total minus residual over total. So what you got and left over, sum to total. And so R squared then is essentially how much variability, how much information did your model capture relative to what is left over. So most of the time people think about R squared as the proportion of variance explained, like by how much did the E variance go down relative to what it was supposed to be. And so you can also think about F in the context of R squared by rearranging the formula to look like this. So here's F. These are F distributions. Do you notice something in common across them, even though they have slightly different shapes? Are they symmetric? Yeah, not most of them. F is a squared metric. So F is never going to be negative. The reason for that is that what F is essentially doing is testing simultaneously if a set of fixed slopes is different than 0. That leaves as a possibility that some of the slopes could be positive and some of them could be negative, and we don't want those to cancel. So for the same reason that we have sums of squared deviations to make the positive and negative e's not cancel, we have F as a squared statistic. So F tends to have a positive skewness. It has lower bound at 0, although practically it's more like 1. And that means that where unexpected starts has to be on the right side. So 5% is past the critical value for F, and whereas in T it was 2 goalposts, in F it's only 1. And the shape of F, where the 5% starts, depends on your degrees of freedom. So the first number in the parentheses is numerator. That's number of slopes spent in your model. The second number is denominator, number of slopes you could have spent that remain based on your sample size. So you can see the shape changes quite a bit based on those things. You don't need to worry about this. It's all baked into the software. So you will get an exact p-value for how likely you are to be to get an F that big if the null hypothesis of all the slopes you tested being 0 were true. So, all right, so let me pause there and just most of this. How are we doing, folks? Can I get a thumb check? Sideways. Okay. The big picture is we're testing multiple slopes at the same time to see how well the model works as a whole. That answers the question, by how much have we reduced the variability in this outcome? How much have we explained? And F is built as a ratio of information gotten, essentially, per slope relative to information remaining per slope. So that we have, did we get a good deal? That means like an F of 1 would be like the lower bound, sort of like what is likely to happen, but you can actually have Fs of lower than 1 if you did worse than chance. I've done that before, not to brag or anything, but I've been worse than chance in some of the models that I built. So in case you're like, what are all the letters? I built this slide for you. And I apologize that letters get reused, but I didn't make them up. I'm just the messenger. So to try to summarize this process of hypothesis testing against the null, what letter you end up with your test statistic depends on your degrees of freedom and whether or not you're using denominator degrees of freedom. So again, critical choices that we have to make ahead of time. How much is unexpected? That's our alpha. Alpha rate is also known as a type of error. Which one is it, 1 or 2? Quiz question from before. Alpha is type 1 error rate or type 2 error rate? Got 1 vote for 1, 2 votes for 1. People are like, oh, which one was it? Lots of abstainers in this quiz. 3 1s. I'll take the 3s. Yeah, alpha is type 1 error. That is false alarm rate. So this is something you set at the outset. What is the false alarm rate you're willing to live with? 0.05 is convention, but you can be more conservative or less up to the standard of the discipline. And then, are you willing to be wrong in both ways or just one? That's one tail versus 2 tails. It's always going to be 2-tailed in my world. And then the question of what test statistic you get depends on degrees of freedom. So, are you paying attention to sample size? So the difference between T and Z, for instance, T is flatter because if you in smaller sample sizes, there's more variability, and where 5% starts is further out. So if you have enough people, T and Z are the same thing. That's what we've seen up to this point. So if I'm testing one slope, it's going to be T most of the time. F is t squared if I'm testing one slope. So that's why the test of the model is the same thing as the test of that one slope. But if you're testing two or more slopes at the same time, such as if you have three categories and you need two slopes to differentiate them, then that's F instead. By the way, not in use in this semester, but something you may have seen, z squared is chi-square. So chi-square looks a lot like F, but it doesn't have a different shape based on sample size because it pretends it's infinite. In certain classes of models beyond this type, generalized models, structural equation models, and some multi-level models, you'll see z's and chi-squares instead in your output, and they don't do t's and f's, but just know that they're very much related to this. So then the rules are the same. If the test statistic exceeds the critical value, the goalposts, F only has one side, then the obtained p-value is less than alpha. We say the result is significant, we reject the null. Otherwise, if we're inside the boundary, not significant, retain or do not reject the null, take your pick. So we will work with T's and F's the rest of this semester, but I just wanted to orient you to how those other letters fit into the picture. All right, so what I said before, I'll say it again. I should assume you don't have perfect recall, right? That's still a reasonable assumption that I say something once and you don't remember it perfectly? Yeah, I thought so. So if we only have one predictor, like homework 2, where you are predicting fits thrown from either pleases heard or age 3 or 4, then the significance test for beta 1 that we looked at a t-value, and again, t is estimate minus the null divided by standard error, t squared is f. So if that slope is significant, the model is significant, the end. Likewise, for an effect size, it's going to be the exact same thing as just a Pearson correlation between the x and y, or more formally between y hat and y, because these two terms build y hat. So the r square would be the same thing as the square of a Pearson correlation. Now it's different. So anytime we have more than one fixed slope, such as differentiating predicted income as a function of working class, F is asking, is the predicted y, so built from this three set of terms here, the y that's predicted significantly correlated with the actual y, and the square of that is the model r square. So it's not that we're correlating each of these binary variables with y. That won't work because they don't mean the same thing when separated as they do when together. It's the prediction that these terms create. That prediction, we're asking whether it's significantly correlated with the real outcome. And so then the F test evaluates degrees of freedom, model R squared relative to degrees of freedom spent in that case. So all together then, like the results for this example data set would have these values in here. And if you're like, is 14,000 a lot? I have no idea. It's based on the scale of your outcome. Like these numbers have no absolute meaning of any kind, because they would shift if we had income in thousands of dollars versus hundreds of dollars versus $10,000 versus whatever. So don't worry about the absolute amounts of these things. It's the relative information that we pay attention to. So information that has been introduced by the predictors, so y hat minus y bar, and on here it never shows up correctly and I still don't know why, divided by number of slopes it took, so there's just 2. That creates this value for mean square, which you can think of as like how many things you bought relative to how much it costs. Then we have leftover, how much variability do we not know yet? So what are all the reasons people make different incomes that are not in the model? That number here is a lot higher. Likewise, degrees of freedom for the denominator. We have room to add 731 more slopes based on our sample size. So information left over divided by slopes left over gives us this number, which is a lot smaller than that one. In fact, it's smaller by a factor of 42, and that's our F. So information captured relative to information remaining gives us the test of this thing. So that's what we would report. And starting in homework 3 and pretty much for the rest of your lives, like the world has agreed on this convention of reporting, it will look like this. F, the 2 degrees of freedom separated by a comma, and then the F value. MSE stands for mean square residual, this number right here. That is the same thing as residual variance. So you're already familiar with this concept. The variance of the E's from your current model, it would go right here. and then the corresponding p-value. The reason that we give those 2 degrees of freedom, so these 2 squares right here, the f and that number, is that you can then work backwards to fill in the rest of the table if you wanted to. So those are like the summary pieces that you need to get the whole thing back together if you wanted. So now we can look at one. So this is what it looks like when you don't have a whole bunch of explanation. This is ours version of it. So this is the same analysis, income predicted by these 2 binary variables for working class. And this is the output from my custom function where I put everything into one table. This type of table is what I'm used to seeing in every other stats package I know. For whatever reason, it doesn't show up in R by default. So I found a package called Supernova that gets me part of the way there, and then I customized it to get to where I want. So in terms of what we pay attention to, this number right here, the 171, that's our residual variance, or mean square error. F is the ratio of information explained over information remaining. The p-value that goes with F tells us that this F is really, really unlikely, unexpected, if these 2 slopes are not different than 0. And then last but not least, R square. So 2 different ways to think about R square, you take your pick. One is this value is 0.103. I would say that 10%, 10.3% of all of the variability in income has been attributed to this self-reported working class variable. I'm not going to say caused by or due to, but I will say attributed to or predicted or associated with. So 10% of the variance has been explained, is another way people would say that. That means 90% is unexplained. Okay, with me so far? Maybe. So 10% is better than 0%. So another way to think about it is in terms of hypothesis testing versus effect size. For the overall model, meaning the 2 slopes working together, the significance test is F, the corresponding effect size is R square. Likewise, down here, we had T's as a significance test with corresponding effect sizes given by a subsequent table that's coming in a couple slides. D's and R's. We've seen those a little bit before. And the rest of this we walked through already, but now we don't have to ignore this table anymore. So let me ask you a question then. Let's say that this is a 5 category example, like we just talked about in the slides, in the little whiteboard thingy. What would this number become, this 2? Yeah, it'd be 4. So then what would this number become right here? Degrees of freedom for the denominator. Yeah, 729, because it's zero sum, right? There's 733 points we can spend. We have 734 people. The 1 is because the starting point is the empty model always has 1 term in it, the fixed effect. So these things are compensatory. As your model gets bigger, add stuff to it, the first number will increase and the second number will decrease.
Can
I talked
I
about
ask a question about our
Please.
previous slide that it may be a dumb question? So the total, yeah, nope, the one we were just on.
Okay.
Hang on. I can, yes. Right, so the 733 as your total.
Mhm.
Where does that total come from?
Sample size.
Perfect.
Yep.
Okay.
Yep, there are 734 people in this data set.
Okay.
Like if we start with like the worst model ever, the empty model where everybody just gets the mean, we had to spend 1 point to estimate that mean. So 733 is like is the worst we can do, and then the question is how do we divvy it up between spent and leftover?
Perfect. That makes sense. Thank you.
Thank you. Yes. Other questions? By the way, this slide has the total variability in Y on it somewhere. Where is that? Like how much variability in income is there, period, to start with? before spending anything except the mean. Yeah, so this essentially is the numerator of how you compute variance for the outcome. This is the denominator, so 190. Yep, so that's another way to look at it, is like this MS column, mean square, it's variances. So it's like this is the total variance, this is the leftover variance, this is the accounted for variance. They sum together. But because we can't just judge like, is this good that we captured this much variance? It's like, well, how many slopes did we have to spend to get to that point? So it's like a weighted average essentially. So that's why we have the numerator divided by the number of slopes in the model versus number of slopes remaining. Okay, other questions or clarifications? Things I can say again also. What's the total variance in income as our outcome variable? Yeah, it's right here. So in the empty model, if you looked at this table, the whole thing is empty except for this last row, because it doesn't differentiate between explained and unexplained, because there's nothing to explain it beyond the fixed intercept that you need to even compute variance in the first place. So question, should we technically be able to see T and F values in all education papers, and we would rarely or never see Z and chi-square? Not quite that straightforward. T and F, yes. So T is for testing one thing, F is for testing multiple things. That is always true. Once you leave the land of general linear models, where everything is based on sums of squares as how you find the estimates, basically someone genius figured out a long time ago that this is an easy way to figure out which values minimize the sum of the squared residuals. Like once you're in a different way of finding the answers, then like as a consequence of that, you switch to C, Z's, and chi-squares instead of T's and F's. But conceptually, they do the same thing. If you're testing one thing, it should be a Z or a T. If you're testing multiple things, it's going to be an F or a chi-square. You will also see chi-squares in contingency tables. So like it's called a chi-square analysis, like when you have two categorical variables and you want to see if the people who answered one in this group are also likely to answer one in another. For whatever reason, that's almost always reported as chi-square, even though there's other measures of association that might be relevant in that context. So I'm not sure if that helps or not, but in this class of models, it's almost always T's and F's. In other classes of models where the answers are found through something called likelihood estimation, then it switches to Z's and chi-squares. And I hope that you all will come back to learn about those higher classes of models, because they're super fun. You just got to trust me on it. No, they're super fun. Trust me. I picked this job for a living. Can you believe that? I was like, nope. As I think I mentioned on the first day of class, when every time I go to the doctor or hospital to get blood drawn, like they make conversation with me, like, oh, what do you do for work? And I say, I teach terrified graduate students, statistics. And that always leads into a story about how much they hated statistics. And I think to myself, well, I hate needles, so we're even. But anywho, let's see. I think this is where I stopped in the video, so we have some new stuff to talk about, or extensions of the stuff, I should say, effect sizes. So we ready for that? Y'all ready for this? I have to get some hype music going. Yes, I was on my high school dance team, and I have things in my head from the stuff, so just forgive me, Yeah, I know. I'm full of surprises today. Effect size, that's where we're at. So we talked about D's and standardized slopes in homework 2 as a way to quantify like how large the association is between one variable and one outcome. We want to do that all the time, but the question is how. So for multiple slopes, we have R square instead. For a single slope, we can do standardized slopes, although I don't like them for reasons that we can talk about later. No, we're going to talk about it now. I foreshadowed. I have another slide that's more in depth that I'm thinking of in my head. So standardized slopes are essentially if you change your variables into a z-score metric, so then each variable has a mean of 0 and a variance of 1. They're on the same scale. Then the slope that results if you stick those variables in the analysis instead is a standardized slope. And in some cases, that's fine. Those are very, very commonly reported. I don't like them. The reason is because they are ambiguous for certain types of parameters, such as, we're going to see this in a couple slides, quadratics, parabolas, bendy lines of various shapes. Well, it turns out that if you have x and you square x, you do not get the same answer if you z-score x and then square the z-score as if you z-score x squared. There's an order of operations problem in there that makes the results ambiguous. The same thing is true more generally for interaction terms. If you want to know if the slope you've just estimated works equally well for everybody, or whether people who are different on other predictors need different versions of the slope, then in that case, you have the same problem. Z-scoring the product of two variables does not give you the same answer as Z-scoring each of them and then multiplying. It is also the case that, and I didn't appreciate this until I read about it in your textbook, that for binary predictors, even if the same mean difference is found, the standardized slope for it switches based on the proportion of people in each category, which seems kind of unfair because the proportion of people, the mean for a binary variable, dictates what its variance is. It's the proportion of ones times the proportion of zeros. So then different proportions create different variances by which to standardize, even if the mean difference is the same. So I don't like that either. So we're going to do a couple other things instead. Please.
For one unit increase,
Yeah, for every standard deviation increase, like the slope tells you how much y changes, yes.
okay, so it's not, it tells you how much change in standard deviation.
It's change in standardized units, which is why people like it. And it is useful if you want to judge the relative importance of predictors in your model, because they're on different scales, right? You have to know what the units are. Like one predictor could be 6 and another predictor's, or their slope could be 6 and others could be 0.6. And the 0.6 could be bigger depending on the scale of the variable that it's tied to. And so it solves that problem, but it also introduces other problems. So I'm not sure if I answered the question. Let me pause.
Yeah.
Okay. The problems that it introduces down the road, and the slide I was thinking of, is in models with multiple predictors, which is unit 4. The predictors essentially compete against each other to predict variance. So if I have two predictors that have a lot of overlap, then the variance that's relevant for standardizing that slope is not the original variance. It's the unique part that's not overlapping. Standardized slopes don't do that. So it's not standardizing against the right source of information in the variable at that point. And so I think the results are potentially misleading. There's an alternative that I like better, which is semi-partial correlation that actually takes into account the unique variance instead. But that's much less common for whatever reason. How do I say this? It's very, very common, and your interpretation of what it means is correct. But I think the inference about the role of the variable in the model has to take into account the unique information it contains, and there's no architecture in standardized slopes to do that. So to me, they're potentially misleading. They also don't, they range from past -1 to 1. They can go out of bounds, depending on the particular configuration of correlation among your variables. So they're not standardized in that sense either. There is a blog post that I linked to in Unit 4. Some guy who hates these way more than me wrote this, and I think it was a very well-reasoned argument. There's also some discussion of this in your textbook regarding effect sizes. So I would say that you can report them, but you might also report a correlation family effect size that's not a standardized slope to keep people like me happy too. Yeah, just add columns to your output to keep everybody happy. Then they can just look at the one that they like and your bases are covered. That's my general strategy. And if not all the columns have room in your paper, then there's always supplemental materials that you can use to provide things with extra space. All right, other questions? So effect sizes then. There are two different families of effect sizes, not just metrics, but families. There's partial and semi-partial. The latter is coming later, so we're just going to do partial for now. This is the idea of what does the slope contribute uniquely relative to like disregarding everything else that's in the model. And we can compute this directly from the model, the t-test for that slope. So this is really useful because then you can compute effect sizes not just for slopes that are in the model, but for any linear combination. So any other model implied slope, like as for the non-reference group differences, you can use this formula to compute it. And I built this into both of the functions that we're using in this class. You can also get it from different packages in R. So there's one metric, R is in a correlation metric. So this is useful for quantitative predictors. D is the one that we've seen so far, and this is more useful for categorical predictors. And I have the word partial in front of it, but no one ever says that. I just want to point out that it's part of the partial family as opposed to an alternative family. Because in order to compute a D, you have to have groups in the model. So D and partial correlation are the effect sizes that we'll start to use in this set of examples. And by the way, you can go back and forth between them. If you get one and you want the other, you get there. So this is what is contained in the GLHT effect sizes equals true option. It spits out this table right here. And I've highlighted the effect sizes for the 3 potential differences among our working class groups. So we have actually, my little box should be a little smaller. I got a little overzealous. I included one of the means, my bad. I'll fix that offline. So if I look at just the D column, these are standardized mean differences. So the first 2 differences are statistically significant. And you would think, based on the size, if you just looked at these numbers, that the second one is bigger. But it's not. It's actually smaller. So there is a bigger standardized difference between lower and middle than there is between lower and upper. Again, the reason is because the upper group only has 20 people. So there's more uncertainty in that. Middle versus upper then has a D effect size of only 0.05, tracking with the fact that it's not different than 0. So a standardized mean difference of 0.05 standard deviation units is all these groups differ by. So not much of a signal there. So that's one metric in standard deviation units. The next column, PR, that stands for partial R, as just introduced. This is in a correlation metric instead. But you can see the same trends. The partial correlation that is a part of this group is 0.3. This group difference is only like not even half of that. And this one is very, very tiny. The last column is semi-partial R square. We're getting to that in unit 4. This one, though, I can tell you more generally, is how much of the R square that parameter is responsible for. So it has a very direct interpretation in some cases, but not always. Yes, you can do a partial R square as well, and you can also do an unsquared semi-partial. I picked these 2 because I believe they are the least likely to be confused. Because once you start talking about R squares, you want to talk about variance explained, but partial R square is not that. It's related, but it's not that. So stay tuned, I guess, is the message. So then effect sizes. So this goes back to power for what? I think we talked about this last time. Let's say that you come to me with this type of problem. I'd like to do a research study. I have 3 groups. I want to see if they're different. Can you help me compute power? Sure, but power for what? Well, here's some possibilities. The first contrast, the slope that differentiates the middle group from the lower group, has an effect size of either 0.31 in the R metric or 0.65 in D, in correlation units or standard deviation units. That means that each group would need to have about 45 people in order to have an 80% chance of finding these effect sizes if they are there. And by the way, these numbers came from the table that I showed last time, and I have linked on your website. Well, 45 people per group, that's not insurmountable. Like, do you think we could do this in research that you're familiar with? Maybe. Well, what about lower versus upper? Now, this one on paper sort of looks like it's a bigger difference because it's a difference of 11 relative to 9-ish. But it's not that big. It's much more uncertain. Standard error is 3 times the size. its effect sizes are smaller. So now I need at least 175 people per group to power this one. That's a little tricky. The last one, even worse. An R of 0.03 to detect at 80% probability for that effect size, you need 2,000 people per group. But what if you're like, can I just like, how much does group matter? Can I have an effect size for that? Sure, that's R squared. So if I unsquare that R, then I'm back in correlation metric, a correlation of 0.3. I need about 85 people. So power for what?
Combine this symbol. Make this a simple loop.
You could. So this result that they're not different, either statistically or based on effect size, then one could do that. And that would actually improve your power because now you have one bigger group as opposed to, two smaller groups. But you would have to somehow justify this based on pilot data or theory or preferably both. Yeah.
Like, say, do this on purpose, would that purpose be interested in running another analysis and trying to figure out how many people want for that analysis, or like what will be the purpose in trying to find points in both?
So the question was, when would I do this in life, broadly construed, or research life at least? I'm making sure to repeat the question because I'm not sure if the microphone is capturing this, since the owl hates me at this point. It hasn't even hooted at me in like an hour. You would typically do this based on preliminary information of some kind for future study planning. So if you collected pilot data, you got some guesses of effect sizes that would help you hone in on how many people you need to do it for real. Or if there's similar enough research that where you can compute their effect sizes and try to use that for planning. That's probably like 90% of the work that would be done with effect sizes for planning purposes. There's also the remaining 10%, what is known as post hoc power estimation, where the reviewer too is like, hey, I don't know that your study has enough power, prove it. And you have to work with the data you already have to demonstrate that you were adequately powered to test the hypotheses that you tried to test. The problem, of course, is that in designs where you have low power, it's because you usually have low sample size, and whatever estimates of effect size you get back are going to be just as noisy as the rest of it because you can't nail something down with only 10 people. So I think the planning side of it is what it's intended for, but like in reality, like this model, not to be like condescending or anything, but this model is relatively simple. I have one X and one Y, and the X takes two slopes. And I have 4 answers as to what I'm powering. Can you imagine how much exponentially more complicated it gets when you have lots of variables and lots of outcomes and like you're trying to do like look at a system of relationships all at once? There's really no way to do it and guarantee that each of those pieces would be adequately powered. It becomes creative writing very quickly. What I end up having to do in practice, because I don't know how to do power, no one does, is not what the reviewers are going to be looking for in your analysis plan, is to simulate data. So I try to make educated guesses about what things would be, and I create fake data. And I do that like 1,000 times from the same population, like the 1,000 samples, and we see what proportion of the time each effect tricks is significant. And so then you have like full control over exactly what the model and the variables are because you build it. But then that's also the case where if you change one aspect of it, the rest of it has to shift to accommodate it. So still ultimately creative writing, in my opinion. I could be wrong. All right, does that help? Planning purposes, final answer.
And might be a boring question, but would trying to find potency or just any effect size be helpful for inference? Does that play a role?
I would say, so Zoomers, did you hear the question? Is it picking up the audio? No? Okay, let me see if I can switch the speakers here. Oh. Well, the problem is the microphone on Zoom is me, so it's not going to pick that up. It's only going to pick up that one. Okay. Well, I will repeat the question. How about that? In terms of I think the question was, do effect sizes play a role in hypothesis testing? So indirectly, yes, because what you're testing is the size of the effect, but it's sort of buried in the sense that like you can end up with a significant result because either you have a large effect or you have a lot of people and a lot of power to find a small one. Like the fact that P crosses the magic threshold doesn't directly tell you about the effect size. And so that's why it's really important with every result you report to include some measure of effect size, not just significance, so that you can see in a more absolute sense, like how strong the relationship is. There's, 30 different kinds of effect sizes though, so then people fight about which one is the right one to include. I view them as like two sides of the same coin. Partial effect sizes, there's more room for misleading your reader. I'm going to say more about this later, but what partial effect sizes do is relative to the variance that's not already explained, like how much did this one get? And so relative to the not explained yet is the problem. In this kind of model, like these R's are relative to the rest of the contrast for group. And so like they all have to fit together and it makes sense. But in other models in Unit 4, where we add different kinds of predictors, then your effect size can change based on how good they are. So let me give you a real world example. We're going to talk about this in the next few weeks, but just to answer the question, let's say very hypothetically that I bake a pie and I bring it somewhere to feed people like a potluck. I don't bake, I don't cook. This is completely hypothetical, but let's say that I did. And half my pie is gone and I bring the other half home. And then my son says, "Can I have some pie, Mom?" And I say, "Sure, but just don't eat the whole thing." And so he eats half of what's left. How much pie did he eat? Relative to the whole, half of what's left, if there's half remaining, he ate a quarter of the pie. That's semi-partial. But if you want to say, no, he didn't have access to the part that the party ate, he only had half of it, and he ate half of the half, like that's partial. So he ate half the pie is a partial effect size. He ate a quarter of the pie that was originally there is a semi-partial. So there's more room for misinterpretation of the partial family more generally. At this stage, though, it's not an issue because these variables are working together and they're not competing against other variables for variance explained. How you doing, folks? Other questions, comments? All right, words. For your future reference, this is how I would describe the results of the analysis that is part of this example. All right, intermediate summary, and then, a slide. Okay, we'll do this, we'll do the thing, and then we'll take a break. How's that sound? Cool. All right, so slide 29, intermediate summary. If you have only one slope in your model, the test of that slope is the same information as the test of the model. So in other words, you have a t-test statistic, because we're using denominator degrees of freedom, of estimate divided by standard error. That t squared becomes f in the test of the model. Likewise, the standardized slope is equivalent to a Pearson correlation. If you square that correlation, that's the model R-square. One-to-one correspondence. If you have more than one slope, that is not going to be true. We don't want to just know if each slope is significant. We want to know if the set of slopes that works together is significant. And that's a more general question of how effective the model is at predicting the outcome. So in that case, we have F for the model that tests multiple slopes against 0 at the same time. We have how correlated the y hat is that the model creates with the actual y, that's R. If we square that correlation, that's the model R square. All right, so conceptually then, let's answer these questions, go over them, and then take a break. How's that sound, folks? 4 questions. Let me open up the whiteboard again. All right, so second slide here, if you'd like to enter your answers for us. It looks like folks have had a chance to contribute. I'm trying to read all the answers and seeing a lot of common overlap. So the first one, what does F tell us? F is more general than this example. F tells us on the whole if a set of slopes is different than 0, like simultaneously. In this specific context, those slopes represent group mean differences. But more generally, F tells us if a set of slopes of any kind together are different than 0. So I'll see an example of that for nonlinear trends of quantitative predictors in the next set of analyses. Model R square. That one, basically how useful your model is. Like how much information have you captured by the predictors you've included relative to what's left over. So it's an effect size that goes with F to talk about just how effective your slopes are, where 0 is the worst they can be and 1 is perfect. So then more specifically, 2 definitions, it's the proportion of explained variance. So by how much the residual variance went down relative to the total. Or if you think about it as a correlation, it's the correlation not between X and Y, but the Y hat that the X's create with the Y that's actually in the data. So, and then power for what? Lots of good answers here because power is relative. Yep, that's one. Each relationship has a different power. Yes. Each effect size is relative, depends on the group referenced, all of those things. There's a whole bunch of potential possible effect sizes for any analysis, and that logically leads to a whole bunch of different levels of power. So we got to know power for what to answer the question. All right, good work, everybody. I think it's time for a break. How about you? Sounds good? All right, let's take 10 minutes. See you back here at 6:20 then. I'll leave the whiteboard open in case folks want to keep reading.